Moving on to Physics C review number 4, we have another differential expression here. There is a cart being pulled to the right by a fan. The fan is pushing air this way, causing the cart to go to the right. At the same time, there is a funnel filled with sand that's moving at the same velocity at any given instant this way, and sand is being poured into a cup onto that cart. So we have a situation where we have a changing velocity and a changing mass, okay, for this cart as it accelerates to the right. So how can we do that? Well, we have to remind ourselves that force does equal the change in momentum per time, and force, that is d mv over dt. And using the product rule, the force of the fan, which is the applied force in this situation, has to equal dm dt times v plus dv dt times m. Now we're going to let c equal dm dt, the rate at which the mass of the sand is being added, okay, to the cart. Okay, and we're going to assume that that's some constant rate that is actually calculatable. Okay, so if we look at the situation, then what can we sub in here? Well, dm dt then becomes a c times any velocity at any given instant, plus acceleration, okay, because that's what dv dt is, okay, times m naught, which is the beginning mass of the cart, because that mass here is a constant value. Okay, so that's a nice substitution there. Now the acceleration, what should that equal to? Well, remember, F does equal ma, but in this case, mass is not constant. But the force of the fan should be reasonably constant, assuming that the speed of the fan is pretty constant and the air density around is not changing. So the acceleration then would equal the force of the fan divided by the beginning mass of the cart plus whatever mass of sand has been added. So what should that equal? Well, that should equal the rate at which the sand is being added to the cart multiplied by time. So that would be the total mass added. So the acceleration is force of the fan times the mass of the cart at any given time. So let's substitute that in there. So the force of the fan will then equal CV plus force of the fan times m naught divided by m naught plus CT. Okay, so a pretty simple expression there. We're then going to just rearrange this expression. We're going to take this expression over to this side. So CV equals force of the fan, okay, minus this expression here. Okay, and then factoring out a force of the fan and dividing by c, we get velocity equals force of the fan divided by the rate at which the mass is changing, which is c, multiplied by 1 minus m naught over m naught plus ct. So that's a pretty reasonably easy explanation for that situation. Okay, let's take a look at another situation. Here we're looking at two different moment of inertia, okay, examples. And again, it seems like we're island hopping a little bit here, topic to topic, but this is just kind of considerations of special things that were going on in Physics C this year. We want to find the moment of inertia of this rod rotating about this axis here. Once again, we see lambda equals m over L, and therefore dm equals lambda dx. And dx is, of course, any infinitesimal x as we go along, you know, this particular bar. And again, we're assuming that there's a uniform mass density here. Okay, so remember that di, the derivative of impulse, or di, is equal to r squared dm. Well, what's dm equal to again? Well, dm is going to equal lambda, okay, multiplied by dx. So we're going to integrate the left side from 0 to I of di, and we're going to integrate the right side from 0 to L, okay, from 0 all the way to the length L. Okay, and this is going to be, of course, r squared lambda, okay, times dr. So we use the letter r for x in this case. Okay, so what are we going to get? Well, we have 1/3 r cubed would be the integral here, but we're going to put in our definite integral from 0 to L. So we're going to be 1/3 lambda L cubed. And now substituting m over L for lambda, we get 1/3 m over L cubed, or 1/3 ml squared. So that would be the moment of inertia for a bar rotating at one end. Now what if we want to consider this bar being rotated through its center of mass? Well, we're going to use the parallel axial theorem. The moment inertia of a parallel axis is equal to the moment inertia about its center plus mass times d squared. And of course, d is how far away you've got your axis from the center of rotation. In this case, the center of rotation here is right located here, and this parallel axis is a distance L over 2 away. Okay, so, or 1/2 L. So what we're going to do, so the parallel axis is our 1/3 ml squared. So this axis is parallel, but not to the center of mass. So we're going to do 1/3 ml squared equals I center of mass, which is this one here, plus ml over 2 squared. Okay. Why? Because this parallel axis again is 1/2 L away from the center of mass. Okay. And if you calculate that out, you're going to see that I center of mass is 1/12 ml squared. So the parallel axis theorem is a very useful theorem to figure out moment of inertias if you've already got something else figured out. Okay, and one more consideration for this video. You know, what if I have a disk of some sort or a cylinder and I want to figure out the moment inertia of this? Well, in this case, we're going to use sigma, which equals mass per area. So consider this to be like an area density. Okay, and therefore dm equals sigma, okay, dA. So how are we going to do this one? Well, consider this. We have this whole disk here. Let's pick a circle here, and then another circle just a little bit wider than that, a distance dr apart. Okay, and if I was to cut this circle and lay it flat, we would get something that looks like this. Okay, it'd be like a little tiny flat rod, I suppose. So we want the area of this rod. Well, the length of this rod, of course, is going to equal 2 pi r as we go around the circle. And then the width between the circles is going to be dr. Now remember, these circles they're drawn a little larger. They would actually be a distance dr apart, an infinitesimal dr apart. Therefore, the length of both sides would be 2 pi r, and dr would be the width between. So then dA is equal to 2 pi r, okay, dr. So that would be the area of this, of these two circles together. Okay. So what do we have? Well, di equals r squared, okay, dm, right? Okay, so what do we have here then? Well, we have dm equals sigma dA, right? Well, dA is equal to 2 pi r dr, and sigma, of course, is mass over area. So what do we have here? So I have di is going to equal sigma r squared times 2 pi r dr. Okay, so this is our r squared, and we have sigma times dA. Okay, so what are we going to do? We're going to integrate both sides of this. di is going to be integrated from 0 to I, and the right side, I'm pulling all the constants out, is going to be sigma 2 pi. We're going to integrate from 0 to r for r cubed dr. So what does that integral equal? The integral, that's going to be 1/4 times 2 pi sigma times r to the 4th. Okay, so let's go ahead and substitute everything in for this. Well, remembering that sigma does equal m over a. So what's the area of a circle? Area of a circle, of course, is pi r squared. Okay, so I'm going to substitute in for sigma m over pi r squared. Okay, and then of course simplifying everything out, a radius squared and a 2 over 4 and a pi, the moment inertia of a disk is equal to 1/2 mr squared.